it starts with a question. And that is where we left our last webinar, which was taken by Professor Somik from IT Delhi, when he talked about why is the sky blue and how that question led to India's first and probably the only Nobel Prize in science in India. This question by asked by C.V. Raman, and that nobody knew that one innocent question could lead to a Nobel Prize. C.V. Raman not only answered the question for himself, but he answered it for the rest of the world as well. And on that note, I would like to begin today's webinar. Before that, I will introduce you to Professor Menon. So, welcome to today's exciting session of Macmillan Budding Scientist webinar series. Like I said, we're about to go on a supremely fascinating adventure into the world of research and discovery. And leading us on this journey is someone that I have been calling the real life Indiana Jones of engineering. I hope there are some teachers at least who get the Indiana Jones reference. Let me introduce you to Professor Arun Menon, Professor of Structural Engineering at IIT Madras. A little about him. Professor Menon started out as an architect and then earned his PhD in earthquake engineering from the famous University of Pavia in Italy. He's an expert in making sure that ancient historic buildings don't fall down, not even during earthquakes. He currently leads a very important research center at IIT Madras called the National Center for Safety of Heritage Structures, where he and his team work to protect and preserve mountain monuments and temples that are hundreds, sometimes even thousands of years old. His work has taken him all over the world, from India's majestic Konark Sun Temple to Madurai Meenakshi Temple, to ancient monasteries in Bhutan, to historic stone towers in Somalia, even to the UNESCO World Heritage Sites in Myanmar and Laos. Like a true adventurer, he does not just study history, but he helps save it. And when he's not climbing ruins or leading global conservation missions, Professor Menon is trekking in the mountains or cooking delicious Italian food. But that's just not it. He speaks the language to give you that authentic Italian experience. So fasten your seatbelts, ladies and gentlemen, and children, because today Professor Menon will show us how scientists turn curiosity into real world discoveries and how solving a research problem can be as exciting as cracking an ancient mystery. Please join me in giving a big, warm welcome to our very own Indiana Jones, Professor Arun Menon. All yours, sir.
Thank you. At the outset, thanks to the Macmillan Budding Scientist program and the invite to be here with all of you today. I really hope this is just a journey of discovery together. Thanks to Mr. Bandyopadhyay for the very interesting introduction. I have very big shoes to fill in, but I just hope the next 30 or 40 minutes that I'm going to show you some slides and some stories will interest you in the process of research and the many things that remain to be learned and discovered and adapted in our lives, in our countries, in our cities, to improve the experience of human life for everyone. So let me share my screen here. Is that visible now? Yes. Is my screen visible? If someone could confirm that, I'll be great.
Very much, sir.
Yes, sir.
Very much, sir.
Yeah,
Yes,
thank
sir,
you.
visible.
Thank you. Thank you.
Yeah.
So, as the introduction went, I teach at IIT Madras. I'm in the civil engineering department, and I work in the structural engineering laboratory. So the laboratory and the faculty members in the structural engineering laboratory deal with structural safety. Why buildings stand, why buildings don't fall. And if buildings were to fall, how do you ensure that you make them safe? Now, what's interesting for me is while I do look at modern constructions, I look at historical constructions. And so I try to work in the field of structural engineering and historical constructions, historical monuments, and what we also refer to as heritage structures, these structures which are a few hundreds to a few thousands of years old. Why do we need to look at them? We need to look at them so that today, we construct very differently, we use very different materials, but then if you want to protect them so that future generations can see these and understand these, we need to be able to understand how our ancestors built. How did they use these materials? How do they build such massive constructions which have survived for several hundreds and several thousands of years? So that's the domain within which I work. And we try to examine, we try to understand how these structures evolved and what is that we need to do to ensure that they continue to exist in a safe manner for many more hundreds of years and enjoy their presence in our lives. You must have seen beautiful monuments all over the country, all over the world. They are awe-inspiring. They make us think how our ancestors might have lived. It gives us a sense of history. It gives us ideas in terms of how materials and structures can be built. It opens an entire world of fascinating exploration. So that's the subject within which I work. My training has been in earthquake engineering, which is to understand what happens to buildings during earthquakes. So most of my research sort of links up to earthquakes and buildings, and in this case, monuments and earthquakes. So what I'm trying to do today is take you through a couple of examples of how a problem is conceived and how do we then start studying? Why should we even study that problem? Is it relevant? Is it important? And then try and develop the entire problem. There are different components that we need to work on. And some of it may be on the computer, some of it may be on different experimental platforms. Do tests in the laboratory, like the tests that you do in your physics or chemistry or biology laboratories. We could, in our structural engineering laboratory, carry out tests. And when we see damage, we understand what could have caused the damage. We try to understand better how the structure has behaved. And that's really what gives us a better quantitative and qualitative understanding of these systems, which were built hundreds of years ago, thousands of years ago. So that's the context within which I'm coming to you. I have actually divided my presentation into two parts, and for specific reasons, I would like to look at an entire building, and then I would like to look at a part of a building and try to understand how a research problem can be developed from an interesting question. So all of us are very curious and must develop that curiosity strongly. And so when you see a specific context and you're working in a certain context, you have questions. You must be able to examine those questions more and more. Try to make the question as refined as possible. And then it's at that stage you then understand, okay, if I need an answer for this question, what's the process I should follow? What can give me a convincing answer to this question? That is where these two examples sit, right? So it's important to talk of types of research and where this sort of a work actually sits. Very broadly, research is divided into different types of research. but then we must also be able to look at what is the process of research itself? How does it happen? So I will begin by speaking a little bit about research. And the two aspects that I will touch upon is this earthquake safety of historical constructions, picking up one particular typology and trying to formulate a problem and then trying to solve and get some credible answers from the inquiry. This particular project was actually what we call a funded project, in the sense we formulated a question, and when there was a call for proposals from government agencies that say, look, you have to do research so that the body of knowledge keeps increasing and we have better solutions to ensure several things, better solutions for the country, better solutions for structures being built in the country, and so on. So there are organizations, government organizations, that will call for proposals, and when we receive such calls, we prepare a research project proposal. It's only an explanation of what we want to do. And if the government agency is convinced that it's an interesting problem, and yes, you can spend some amount of time and you will need some resources, which means you will need some funds to actually explore this problem, then the government institution is convinced and says, okay, here, take some money and you can actually work on this problem. So the Department of Science and Technology, in this first case, received our proposal, examined it, asked us tough questions, and then finally said, okay, look, over a 3-year period, try and give us some answers. And this is what typically happens in educational institutions. The government comes in to fund research, and that is how the body of knowledge keeps increasing over time. We call this funded research. But at this stage, let me also tell you, we are able to do a lot of research because we are able to have a collaborative team. We are able to work with students. We are able to work with other researchers who are interested in the subject. And this first work that I'm going to be talking about is not purely my work. It is a work of a team that I led. And the 3 names that you see here, Dr. Bhaumik, Dr. George, and Mr. Sampson, actually worked together to carry out this project over a period of 3 years. The second problem is more on one part of a building. You know, we tend to work at multiple scales. Sometimes they are microscopic scale. What we are working on might not even be visible to the human eye. In some cases, it's part of an entire building. In certain cases, it's the entire building. So the first problem is an entire structure. The second problem is part of a structure. And then once we understand the behavior of what we are trying to study, we then try to see is it behaving well? Is it behaving inadequately? Can we improve the behavior? And if we do that, then we also create a way of engineering a better performance. And that's where technology comes in. And then this can actually be given back to the society, and you can actually say, look, you can improve the behavior of such systems by doing this. And that is where new technologies come, patenting comes, and so on. So I brought in the second problem to talk about how we can look at our history, try to learn the way our ancient builders built, but try to see if there are some issues in today's context that may be an inadequacy, and then try and improve it so that we are able to preserve these buildings for a much longer period of time. So the second problem really talks about such a problem, such a context. And here I would like to place on record, again, the funding that we received, in this case from the institution, IIT Madras, are supported by the Department of Education, the Ministry of Education, or the Ministry of Human Resource Development earlier. And the work that I'm talking about was actually carried out by my PhD student, Krishna Chandran, here. So that's a little bit of an introduction on how the presentation is structured. I said I would begin by talking about different types of research. You know, many of you must have listened to different people talking about research. Many of you may be doing research, and the research broadly in the domain of sciences and technology and engineering falls into 3 broad categories. Could have fundamental research, we could have transformative research, and we could have translational research. The fundamental research is almost research for the sake of a better understanding, a better scientific understanding. You're going deeper and deeper to understand how these things function, why something is going wrong. Most of the sciences work in the subject of fundamental research. So that's, you want to understand the composition of some materials, you want to understand why that type of a natural material was formed. All that is fundamental research that typically happens. Transformative research is you, through research, through some innovation, really change the way we are doing things. Today, we are talking so much about wind energy and solar energy, right? We are able to tap this energy so much. Although wind and wind and the sun's rays exist in the environment and have existed so from time immemorial, but we've had to actually understand these systems and create ways of tapping it and then scale it up for use or by human beings, and in the process have ensured clean energy, right? So that type of research is an example of transformative research. It can really change the way the world is functioning. The third type is translational research. So there's something happening in a given field, and there are some discoveries, there are some innovation, but then you're able to examine the application of it in a very different field. There are constraints in the new field, but you're able to translate it. And this type of research where it goes from a certain domain, gets customized for other domains, and then changes the way we do things in the industry is translational research. So broadly, these are three areas of research. Sometimes your research might have some component of fundamental research and some component of translational research. So these are all possible. Now, if you look at the process of research itself, right, each problem that you take on, you really have to understand the context of the problem. Why is it important in that particular situation? We call that the need identification. You really have to understand why is it important for that domain that you have to work on this problem. So the need for the problem, the need for research problem has to be identified. That's the context. And then it is almost the case that somebody has worked on this earlier. You know, it's a world of almost 8 billion people, right? So somebody would have worked on this somewhere, or somebody would have worked on something similar to this somewhere. So you really need to do what is called a literature review. People might have written about it. People might have written books about it. People might have written what are called research papers about it. People might not even have written anything about it, but probably talked about it. So you really need to take some time and understand if this problem the problem that you're thinking of has actually been addressed earlier, right? And we try to spend some calm time in understanding what others have done. And then we arrive at, okay, look, the others have done something like this, but it doesn't solve the problem that I'm looking at. That's when you identify a gap. Because the purpose of research is to increase knowledge, increase what we know, right? And we want to know that because we've said, if I know this, I'm able to solve a certain problem. So identification of the knowledge gap is very important. And for that, the review of literature is extremely fundamental. Once you do that, we get into a stage called hypothesis development. So you know the problem. Now you are asked to state the problem properly. So stating the problem itself is the first part of your research. The most fundamental, probably the most difficult part of your research is to be able to state properly the question itself before you go ahead to solve it. So getting the question right itself is half the problem, solving half the problem. So at that stage, you say, okay, this is my understanding of the problem, and possibly this is how I should be able to solve it. So you create a hypothesis. You say, this is why something is not working. Or this is why we don't know why something is working. So you've created a hypothesis, and now you start exploring deeper and deeper into that particular problem. And you give a solution. You give an answer. You give a solution. But that's the research doesn't stop there, because now you have to come and say, okay, I've said this, but you need to validate it. You need to show that it is right scientifically. And that's the validation phase. And once you've done that, you've sort of answered a certain question scientifically, but you can always take it to a development stage. That's why we call research and development as two important parts of the same domain. Now you should be able to make use of that information and develop it into something that is useful for the field, for the industry, for the people, because we are always looking at a certain context in which this is happening, and we are trying to see how this can solve a certain situation. Today, for example, the batteries that we make may be working at 60%, 70% efficiency. We have a problem. We need to make it run at 100% efficiency. Is it possible? Research is required for it. New materials have to come in. But it can't stop there by just identifying that if you make materials in this way, or if you use these materials, you get better performance. From that stage of the scientific knowledge that you have developed, it must go to the development stage. It must go to the product development. So that is the final stage. And so that makes the research meaningful. It has given a new it has given life to a new product. It has given life to a new way of doing things. And that's when the research sort of comes to a close. You've started with a question, you've answered the question, you validated it, and you've said, okay, now we have something that works better, right? So that's how the process of research functions. So for most problems, you might be able to see this entire cycle. Whether it's going to the development stage or not depends on whether you're doing some transformative research or translational research or fundamental research. In fundamental research, no one's going to come and ask you, okay, you found out about this, how do I take it to the market? No, in fundamental research, it can stop with answering that question. Okay, having said that, let me go to the first problem. I would like to take about 10 to 15 minutes per problem so that you get a fair idea of what we're talking about. So since I work in the subject of historical monuments, we keep asking ourselves, as I said earlier, historical monuments and earthquakes. You keep hearing about earthquakes and you keep hearing about structures that have been damaged. And now you can imagine if you have a monument that's been around for 1,000 years or 2,000 years or a few hundred years, and then there is a massive natural disaster like an earthquake, and you lose this structure. Then who is to lose? We as human beings are the losers, because we have lost a part of our history. We have lost a possibility of looking into the past and understanding how our ancestors lived. So it's very important for culture. It is very important for continuity of the civilization to be able to preserve these. Okay, and that to preserve these are buildings, these are structures. You should know how they behave when it is struck by a natural disaster. And you should have means of, you need engineers to be able to protect these. So that's the whole context, right? And in this case, we were looking at mandapas. You go anywhere in the country, you see a lot of mandapas. Our focus was particularly on South Indian mandapas, and that's why we're calling it in your history. You would have learned about the Dravidian movement, the Dravidian structures, the North Indian structures, and so on. So the Dravidian temple architecture is what we are focusing on. And you have these halls, which are 4-pillared, sometimes 16-pillared, sometimes even 1,000-pillared. So they are very complex. They can become very complex structures. We looked at the simpler ones, of course, because you can't start off with a very complex structure. In this, there are multiple parts. As you can see, there is a plinth, there are pillars, there are beams, and on top of beams, there are lots of stones that are placed as slabs. And in South India, granite is a type of stone that is available in abundance, and you can find it in several parts of South India. And most of these constructions are made in granite. And mind you, they are all single piece of stone, column, single piece of stone, a beam, single piece of stone, each part of the slab and the roof slab and so on. Okay, so they are monolithic meaning one piece of stone. Now, that was the type of structure we are looking at. But what's interesting is, if you look at South India, these structures are just constructed by placing the beam just on top of the pillars, and the slabs are placed from one beam to another beam. So they just placed one on top of the other, like a pack of cards. And we realized that they're not connected to each other like Lego blocks, or they don't have any steel sitting there, which is acting like a connector. So as you place heavy material one on top of the other, the joint has friction, and it is the friction that is actually holding the structure together. Under gravity, it's all okay, but if you were to give it a lateral thrust, which can happen during an earthquake or heavy wind forces, this can potentially move. And so this was really the question with which we began working. Now, I was talking about South India, then he said, okay, let's look at what happens in different parts of the world. And then if you look at a little broader perspective, you go to earthquake zones where earthquakes are quite prominent. So if I were to go to Nepal, where earthquakes happen frequently, or if I go to Gujarat, where the Bhuj earthquake, the region of Kutch, is rather earthquake prone, you have similar structures. And in the past, we've actually seen many of these structures just collapse, and then you lose history. You can go and reconstruct it, but if you reconstruct it, it's no longer the original. You've lost the original and you're making a replica, right? So you can actually lose a lot of information. And the two pictures that you see here is when I was doing my master's at IIT Madras several years ago. The Bhuj earthquake happened, and I had the possibility of going and seeing collapse of some of these structures. You can see what happens to a structure like this, which is also a mandapa, completely lost, right? This is again in 2015 when there was the massive earthquake in Nepal. I had the opportunity of going and having a look at some of these structures, and these are what you see remaining, structures gone. And so in heavily earthquake prone regions, you see these structures collapse. Right? And if you look carefully, you can see some sort of a connection, right? You can see a depression and a projection. So these structures have actually had some sort of a way in which they can be protected, but still they have collapsed, right? And if you come to South India, these structures don't have any sort of joint. They're just sitting one on top of the other and depending on friction. So the concern is, even though we are talking of regions which are of low earthquake occurrence, if they are going to stay there for hundreds of years, once in their lifetime, twice in their lifetime, they may be shaken by an earthquake. And if that happens, are we going to lose these structures? Because these structures don't have even the minimum connections that these other constructions in earthquake-prone zones seem to have. So that is the inquiry. That's the context. That's our concern. Now that's where we've started formulating the problem. So what was the problem? Well, in zones where earthquake activity is moderate or low, there are historical constructions that are similar, but without any connections. If there is an earthquake, a surprise event, will we lose these constructions? That was the basis of the question. So with that question in mind, when you don't have these connections, will these survive? Till what level of earthquake shaking will this survive was the question. So we went forward. And as I said, we have to identify knowledge gaps, right? So then we started reading a lot about it, trying to look at similar contexts the world over, did some calculations, because we know how these structures may behave, so we can make some simple calculations. When you study structural analysis, very much like what you learn in physics, you're able to understand how these structures will shake, and when they shake, what can happen. There is inertial force generated when there is an earthquake. The inertial force is nothing but the mass of the structure into the acceleration of the ground. So we are able to find out how much force is there, and then we see under this force, is this fellow going to collapse? And some initial work actually showed us that things don't look rosy. Things can collapse. And so that was the basis of the inquiry. So we did a lot of this, what we call literature review, to be able to identify the knowledge gaps. So our fundamental question was, how vulnerable are these structures in low to moderate seismic regions? Seismic meaning earthquake-prone regions. So with that question in mind, we said, okay, now let's write up a proposal and put it to a funding agency. We did that, and then we were able to get some funding to take this. The calculations that we did showed us that things may not be okay. So we have to really validate it. So how do we validate it? Can we make an earthquake happen? No, I don't think we can make an earthquake happen. It's a natural process. But we can try to replicate earthquakes at a small scale. So we can make an experiment where we shake the structure, and that can validate whether we got our calculations right or completely wrong. So that's what we did. So we created in this project, we said we will develop a full-scale model, but then I can't build this model of a mandapa, which is a historical construction, like I build concrete structures today or brick structures today. It has to be very much like how it was built in the past. And what do? We go and find sthapati, a person who is trained to make structures in temples. We get a sthapati, also called a sompura in other parts of the country. So they know how to dimension these and they can construct it for us. So we got a sompura or a sthapati, a traditional architect, to come and construct it. And they have rules of how much the column must be, how much the plinth must be, how much the roof must be. And he constructed it for us completely. He made 2 models actually for us to play around with. And then there are always multiple things scientifically that one has to look at. So we decided the size of the structure and started constructing it. I'm showing you some pictures from our lab. The base, normally these structures are built on sand and so on, what we refer to as an earthquake simulator. We have an earthquake simulator in our lab in IIT Madras. We built this model on top of the earthquake simulator, and then the traditional mason built it for us completely. So you can see the plinth level sitting on sand, and then the columns are coming up, and then the beam is placed, the roof slabs are placed. All this is in granite, mind you. And then once everything is over, we fill it with concrete, lime concrete. Lime is a material used for construction, and that's a traditional material that's always been used. So lime concrete is used and filled, and then there you have the structure completed. So you see this blue box on which the structure is sitting, that's the earthquake simulator, meaning it can actually simulate earthquakes that you want to generate, want to subject the building to, and it can be as much as you want it to be. So I can generate a small earthquake, I can generate a large earthquake, and of course only the table will move. The building in which, or the laboratory in which it is sitting, will really not be affected. It's only the model that will be. So it's very convenient. You're not creating an earthquake, but you're creating an earthquake, right? You're creating an earthquake sufficient to make that model that you want to study collapse, but you are safe. The building is safe. You don't damage the structure. And the test is carried out on what we call a shake table. It's a very simple name. What is it used for? It's used to shake buildings, models of buildings. It's called a shake table or an earthquake simulator. And in our laboratory here at IIT Madras, and if some of you visit us, we can show this simulator to you. IIT Madras conducts an open house every year in January, and there are thousands of people who come to see all the facilities inside the institute. And we keep this facility running so that people can see what the simulator can actually do. So this is a 3 meters by 3 meters table, and it has 2 hydraulic arms that can actually shake this whole structure. And I can build a model that is about 10 tons in weight, and it can shake and take it to collapse. So that's the simulator. So now what do? Since we are actually doing a study, we should be able to measure how much the structure is moving. So we instrument the structure. We have to then decide, okay, these are all the instruments that I want to put on top of the structure. So you see this picture with all these all this nomenclature around blue and red. They are nothing but sensors. So we put a series of sensors so that we are able to understand how much is the structure shaking. We also carry out other tests on this before it is damaged, after it is damaged, and so on, right? So it is almost like the doctor is going to work on the patient, and before that, all the tests are done, and all the wires are attached, and now we can go ahead and do the test. So what do? We pick up an earthquake signal from the past, one of the past earthquakes. All earthquakes that happen around the world are recorded. So you actually have the earthquake shaking in 3 directions, X, Y, and Z directions. We have all these records. You can go to databases and download this. And this is what an earthquake will look like, right? For 50 seconds, the ground is shaking. So we have the acceleration record in the 3 directions. We take that. We went and took an earthquake that happened in Europe, Montenegro earthquake of 1979. By the way, that was 2 years after I was born. So this is a very ancient earthquake. We picked up that earthquake. And so what we do now, we have one model. We start shaking the model. slowly with the same record. We scale it down and then we scale it up slowly till we reach collapse. So that's why you see we're doing this test, run 1, 2% of the shaking, run 2, 5% of the shaking, run 3, 10%, till run 11 when it finally collapses. And with all the instruments, we're able to measure what is the maximum shaking at the table, what is the maximum shaking on the roof of the structure, what is the maximum movement of the structure, and so on. So that's how the problem is defined. And we keep doing. If you have one model, you do all the tests on that model. But if you have the luxury of two models, we had the luxury of two models. We try to see if you're getting the same results, because replicating is very important for scientific confirmation that what you're doing is right? So, because the first time it may be just chance, but if you're able to do it second time and then think through it, then maybe you got it right. And so this is an example of how this test looks. This is a video. So you can see the table is moving and the model on top. It's all held up because when it falls, it's just going to fall all over the place. So just for safety, we are holding it up, safety harness. So you see, it moved, and that was just in a few seconds. In a few seconds, the structure actually collapsed. So the picture that you see, and then we are all standing away. We are not standing too close to it because things can fall, and we are actually, structural engineers take pleasure in seeing things fall. And this is in a laboratory, and so everything is controlled. And if we are able to see something fail exactly at the value that we said it will fail based on calculations, we are the happiest people on earth. Okay, so we take some joy in collapse, you can say. So what a picture that you see here is just before, like an instant before collapse. So it's very important for us to understand in what way is it moving? Where is it failing first? So we use cameras, we record all this, we try to understand what's the mechanism of failure. Because if you understand the mechanism of failure, then you're able to strengthen it if necessary in that area of weakness. Okay, so that's what it is. So this in different runs, as I said, as we keep scaling up the acceleration, at some point it would fail. And so with all the instruments that we have, it's recording what's happening. And the pictures that you see here, for example, between run 9 and run 10 is when we realized the structure is almost going to collapse. So run 9, it worked. But then when we went to run 10, much more severe response. It slowly started opening up. The joints, as you know, there's no connection there. It's just sitting. It can just open up, rock, right? There's no connection. Opens up. And at some stage in the movement, it's unable to come back. And that's the point that triggers the collapse. So our intention is to be able to get that. And we got that. Here you can see just before it collapses from the top, we've got cameras everywhere, right? We really need to plan all that. Where do you want to keep up? Because the test is going to run for a few seconds. Within those few seconds, you should be able to capture everything. So we've got multiple cameras, and all this requires some amount of planning and funds. And that's why we write a proposal. And that's why we value all this a lot, because the public is giving us money to do this sort of a research. So this is just the instant of collapse. Why do you need so many pictures? Why do you need so many videos? Because then you can see the sequence of failure, and then you understand, okay, this part of the structure is actually working, this part of the structure is not working, where can I improve, and so on, right? Now it doesn't stop there. You've done an experiment, but can you do it on a computer? Can you simulate this on a computer? Can you do this using simple hand calculations? That is important, because that demonstrates that you've understood what is happening. It's not a black box. Okay, so we try to develop a computer model. Some details here, but I just want to show you what that model looks like. So on a computer, we try to simulate this. It's called a numerical model. We develop this numerical model, and we try to subject this numerical model to the exact earthquake excitation that we put on the shake table. And then, if you're lucky, the results match. Sometimes you'll have to do some back and forth, calibrate your model, and so on. But we feel great that a numerical model of the real structure is able to give you similar results, and that is a good confirmation for you because you're in a better place to understand what is happening. As I said, not only a computer model, because computer can do a lot of complicated calculations simultaneously, but are you able to do that with hand calculations? A simple understanding is very important. So we tried to make a simple model. The cartoon here is a model of the mandapa just before its collapse. So we can use different methods. Here we use a method called limit analysis. That is, at the point of collapse, at the point of mechanism formation, that some joint is opening up and about to overturn, are we able to write the equilibrium equation? You use equilibrium equations a lot in physics. This slide is nothing but writing the equilibrium equations. I'm applying a displacement and the structure is moving. The structure will resist that movement. And so there is a force, there is a reaction. Are you able to quantify it mathematically? And then at some point, it loses equilibrium, and that is called the collapse multiplier. And that is nothing but the lateral force at which the structure has collapsed. So if you're able to quantify that, that's a great thing. Now, I showed you photographs from different angles. Why is it important? Because depending on where these joints are opening up, you can actually have different answers for your calculations. So that's why we have tried to keep looking at what's happening and see if our numerical calculations or hand calculations match these two situations. And when we did that, we found we had to really match our calculations to exactly where the joints were rocking and opening up. And it was this third configuration. Very interestingly, if you remember that video, that picture near the video, one of the joints opened above this corbel and the other joint opened below the corbel on the opposite side. So as it was moving forward, the forward segment opened below, the segment at the back opened at the top. Now, all our calculations, we kept doing it either at the bottom or at the top, and we were getting wrong answers. It is only when we did this, exactly how the physical model behaved on the shake table, results matched. So this actually gave us a good understanding through a complicated numerical model and a simple numerical model by hand calculations of how such structures behave. So the first part, very quickly, we were trying to understand how these dry stack stone pillared, we call them post and lintel because you've got posts and you've got beams and then slabs. They have no positive connections. We knew that these were vulnerable. We wanted to quantify how much it is, right? So we did what we call the shake table test. It's dynamic because it's dynamic, it's time variant. It runs for 50 seconds, lesser than 50 seconds. And we found how it actually behaves. Now, having validated a model, mathematical model, we can extend this to much larger configurations and confidently predict how the system works. So it gives us confidence on being able to check the safety of such constructions and check this for different areas of the country. In South India, it gave us an understanding that if you look at how much earthquake shaking can happen in South India, these constructions have survived because the level of shaking required to make them collapse typically does not occur. That's the reason why these have survived so many years. But if you keep them, if you look at a longer and longer lifespan, the chances of larger earthquakes over a longer period of time is not impossible. But if you go to highly active earthquake zones, like I was mentioning Nepal or Bhuj in Gujarat, you need to have something that actually holds this together. Interlocking is important. Like you saw the one in Nepal, which had collapsed, but there is interlocking. And even the interlocking may be inadequate in certain cases. So this was what we learned from this one study that looked at an overall structure. I'll quickly show you another one, which is at a much smaller scale, just one part of a building. In my slides, and I will share this with the organizers, there is a document, there is a paper that captures this entire study. And if some of you are more interested in trying to understand what we did, look at the scientific aspects more clearly, you're welcome to download this paper and have a look at it. The second one is again dealing with historical constructions, but a part of a building. It's actually part of a floor slab construction, a very common floor slab construction in in South India. It's called the Madras Terrace construction, and it gets the name Madras Terrace construction because it was very prevalent in the erstwhile Madras presidency. So prior to independence, a large area of Andhra, parts of Kerala, and Tamil Nadu, they're all clubbed into what is called the Madras presidency. And this was a very common construction typology in the Madras presidency. Now, many historical constructions have these floors, but over the years, they get damaged, there's deterioration, there is aging of the materials, and very often we just take them off because they're quite cumbersome to make, and many of these materials are quite expensive today, like timber, which is different types of timber that today may be pretty expensive and prohibitive to purchase. But they are very beautiful constructions, and if they are maintained well, they can last for a very long time. So you can see how these bricks are placed on their edge in a diagonal fashion, and then there is lime concrete that is put on top, and this is a very beautiful construction. There are few people who can construct this even today. There are specialist masons who can construct this today. So, but what is typically happening is, since India is developing at a very fast pace, all old buildings that really are run down, we tend to pull them down and then construct new buildings. But when buildings have historical value, it's important to preserve them as much as possible, but preserve them in such a way that they are structurally safe, that they don't collapse or get damaged in a way that the occupants are affected. So the structural safety is paramount, and it's important to understand, even in this particular context, if there is earthquake shaking, how do these what we call them diaphragms, it's a floor diaphragm, how do these floor diaphragms behave? So that was the inquiry. Our intention was, there is a segment of people who've been saying that if there is an earthquake, this behaves very poorly, and then the building can get damaged, so remove it. So we wanted to really examine from that perspective, is it really performing that badly? Or can we repair it in some way? Can we strengthen it in some way that it can survive even some small amount of earthquake shaking? And if that's the case, if small interventions are sufficient to make them safer, then we might be able to save this typology and preserve this typology so that future generations and current generations can look at this beautiful system of construction and preserve it as much as possible. So that was what was happening. It's very interesting that you can just remove this timber rafter. You can see the gaps in the walls. You can just pull them out and replace them if they are deteriorated because of moisture or because of termites, which may come and damage timber. So this is the typology. And what's interesting is, there are codes available in the country called the Bureau of Indian Standards, BIS, the IS mark, which is a standardization mark. There is, in fact, a standardization, a book, one of the codes which talks about this construction, the Madras Terrace construction. So it is quite well understood how this has to be constructed. But its performance under earthquake loads is a gap. So we really have to understand if there is a knowledge gap. And that knowledge gap is what we are trying to formulate within a research problem. And in this particular case, we really want to understand how does this behave under the gravity forces are always there, but earthquake forces come very briefly and come very infrequently. So if they come, how do they perform was the inquiry. So in this particular case, a floor diaphragm, this is a complicated slide, but I just wanted to tell you that it is possible for us to understand how these systems function mathematically and physically. And also understand if you have a very stiff floor diaphragm versus a very flexible floor diaphragm, how does it affect the behavior of the structure in an earthquake? Okay, so that is at the basis of the entire theoretical problem. Now, what we have realized based on past research, I said it is important to look at past research. Past research has shown that if you have a diaphragm which is very flexible, let's say it's a timber floor. A timber floor is quite flexible in its plane. If you take a concrete floor is very rigid in its plane. These two are sitting at the two ends of the spectrum. But there are many typologies of diaphragms that are actually sitting between this flexible diaphragm and this rigid diaphragm. We tend to classify them as semi-rigid or semi-flexible diaphragms. These diaphragms are problematic because when there is an earthquake, they tend to amplify the earthquake shaking and can become detrimental to the building itself. So that is where the problem was. These figures you can see in one case, this is a graph that is showing that the displacements are increasing, and the displacements are increasing for the central region, which is between stiff and semi-flexible. Rigid diaphragms to flexible diaphragms are really not so problematic, but in between lies the problem. And what we realized is that this Madras terrace type of construction sits right in the middle, which means you have a problem at hand. So we have to understand this better. And how do we do that? We developed a full-scale model. We got a traditional mason again come and design this floor for us. And you can see how this is an engineer prepares a drawing and then works with the stapati or the sompura, and then this is constructed in the laboratory. So the picture that you see here on the right is the construction in the laboratory. You have the supports, then you have the timber rafters, and on top of the timber rafters, the entire slab with the brick placed on edge and the lime on top is prepared, and you have a full-scale test specimen. So in the previous thing, you saw a full structure, and here you're actually seeing one piece of a structure. And this is tested. So when we did this test, so what do you do? It's an earthquake, so it is lateral forces. Forces come from the side. So when we subjected this to a lateral force, we saw something funny that was happening, which is all these timber rafters that you see. You know, it is a small red mark there. These small timber rafters, they started moving relative to each other. They started sliding. Okay. So in a way, we saw that this whole slab is not working together. Under gravity, they were all working together. But when there is a lateral force acting on them, they tend to slide because there is really no connection between the timber rafters and the brick and the lime concrete on top. So we said, there is the problem, right? This is a nice cross section. You have timber and then you have brick, and these are not working together. They're just working together under gravity. But if you impose a lateral force on it, they just, they disintegrate. And that was a problem, because if they disintegrate, then the forces are not going to be transferred back to the walls, and you have an instability problem in the building during the earthquake shaking. So what did we do? We said, okay, now if that's the case, the problem is these rafters are not connected to the portion above in brick and lime concrete. Let us try to do that. So we said, let's apply our mind. What may be a good way of retrofitting or strengthening it and upgrade the performance of the lab? So we did that. We took small anchors. There are different companies that sell metal anchors. So the red dots that you see are anchors that go from the bottom into the brick and concrete layer, and you can lock them. This is very simple because you don't have to dismantle anything. You just have to install them in the dry condition and they are locked, right? And you can actually calculate how many are required and so on. So we did that. We just installed these anchors, we bolted them, and then it was very simple. They were not even visible. You can actually hide it well in the construction. And then we tested the slab again. So we tested in the original condition, and later we tested in the as-built condition. I mean, in the what we call retrofitted, which means it is strengthened and its capacity is improved than much before. And so we did the test again, and this time we saw that the rafters are not sliding relative to each other. They are moving together, and they take the overlay, the brick and the lime together. And so you have a bigger cross section that is now resisting the lateral force due to the earthquake. That gave us a lot of confidence, and it said, look, this typology of construction has a lot of capacity. So from something that is just sliding to something that is now nicely resisting and responding in an integral manner was what we saw. So we did that. We actually compared the built, the as-built is this black line, and the strengthened one is the red line that you see. And this is nothing but a load versus displacement, a behavior curve. And it really shows that you can, by small anchors that are installed without dismantling the system, you can change the behavior under lateral forces significantly. And so we have a way of telling the industry, look, don't dismantle these floors in historical buildings and put reinforced concrete slabs there or steel slabs there. You can merely retrofit these, save a lot of money, but make the structure much safer. So that was what we did. And as I said, again, you can't stop with the experiment. You have to be able to analytically and numerically replicate what is happening, because that gives an idea of your understanding of the research problem. So we did a numerical model, and we were able to replicate the experimental results that we saw in the laboratory. You can see some pictures that show the replication of the behavior on the computer simulation versus what actually happened to the structure. And then, as a structural designer, you should be able to understand what any client will ask is, so how many anchors should I put? So you should have a way of calculating how many anchors are required based on the behavior of these systems. And that gives us confidence that it can behave well. So we did that. So what did we really do here? We looked at a traditional knowledge system. In the past, our ancient builders were constructing like this. And we looked at the current context and the problems that we face in the current context. I'll tell you a simple example. In a place like Chennai in South India, Chennai about 25 years ago was in a lower earthquake zone as far as the IS codes were concerned. Today, it has gone to a slightly higher level. And so everybody is examining buildings and saying, okay, for the new level, these are all unsafe. And so they try to remove and put a concrete slab. In the process, we are losing historical constructions. We're losing historical elements in these buildings. So this is a way of re-engineering the understanding of how these structures work. This is a re-engineered version of the traditional Madras terrace slab with a small pin that is introduced, and we work out the process by which it can be carried out, and we get what is called an integral action. The timber was not working; they were like friends who were fighting. The timber behaves on its own, and the brick and the concrete behaves on its own. They're not working together. By installing this pin, we've actually made them work together, and that increases the capacity tremendously, right? So that's what we try to achieve here. Again, since it's a useful intervention that can be replicated in the industry, we have applied for a patent because it's a very simple intervention that can improve the behavior of such constructions. Again, there is a paper, and if some of you are interested to understand more, you can write to me or try to download this paper from the link that is given, from the details that are given here. So again, all I wanted to do here, close, is historical constructions. Research in this area helps us look at how our ancestors built and why they built it in that way. What materials did they use? Why did they build it in the way you see it? Do those things work even today? Or does some improvement really help? Today, there are different contexts of loads acting on these structures. These constructions have lived for so many hundreds of years. They're quite sustainable. They're energy efficient constructions. So it is good if you're able to preserve them and continue to use them. And this is one of the sustainable development goals, that you reuse as much as possible, preserve and reuse as much as possible. And the research contributes to that sustainable development goal. So in this, you saw this strengthening methodology and the improvement in the behavior that we were trying to see if it works or not. So with that, I stop. I know I have exceeded the time that was given to me, and I'm open to questions if there are any at this stage. Thank you.
So nobody complained, even if you've exceeded by a little while. I don't think anybody has complained. I have not received a single remark on the chat box.
I saw my clock ticking away. Yeah.
Okay. On that note, I'll request that for all of you who've been so attentive for the past hour or so, if you could turn on camera, we'll have a quick 5-minute interaction. This is your opportunity to ask as many questions, because unless you ask questions, the fundamentals of science is that unless you ask, you do not know. And as we learned in the last webinar, that a simple question, a simple innocent question like, why is the sky blue, led to India's only Nobel Prize in science. So I request, if you have any questions, could you please turn on the camera? We'll have a quick 5-minute introduction, and then I'll share the link from which you could download your participation certificates for the webinar. Okay, there's a question in the chat box, sir, if I may read it out for you. Uh, this is asked
Sir,
by.
I have a question.
Yes, please. Yes, please. Could you turn on your camera? I'll put you on the screen.
Sir, yes, sir. Sir, myself, Sankar Shah. I'm from the Kolkata. So when we are talking about earthquake, just I have a
One
little bit
second,
because we were
please.
talking about the timbers.
One second,
Can
please.
you hear
I
me,
will.
sir?
Yes, I can. Now we've put you on spotlight so that everybody can see you. Yes, Mr. Shaw, please ask your question.
The question is that, sir, when we are going for the making the structure, nowadays when we use the TMT, we are talking about the timber. One of the structure when you are making, then you use the timber, okay. And whatever the figures we can see here, but TMT nowadays we are making thermomechanical treatment, sir. The core we make soft. So during the earthquake, it is not break, sir. Which we will show, which the in your laboratory when you did the demonstration. I think it is in IIT Madras. Some of the engineers are standing, and the roofs are the hanging over there, and the pillars still remain same. So nowadays we use the TMT thermomechanical treatment. That's why we can say seismic resistance over there, because when we are quenching the TMT, so we are quenching, the upper surface will become hard, and the lower middle one, it will remain soft. So this is a very good session for me because I am a physics person. So very good. So my only one request, if there is any information related, any books or any other things, if you'll get for school level, because I am teaching in the school level after 12 in my school level, because sometimes we are teaching all the things, but we are not getting sufficient time to go for the different lab in school level, sir, I'm talking. So if we get some information that we can show at least, because we have a virtual lab nowadays. So if you think any sustainable materials, if you supply, then it is good for us. That is my point. Thank you, sir.
Thank you. Lot of resources are available online. Today, there are a lot of videos and a lot of recorded lectures on NPTEL, National Platform for Technology Enhanced Learning, NPTEL websites. All the videos of full courses are available online. In that, there may be some parts which will be relevant even to school students, but there are a lot of resources online today that you can look at. And as you rightly mentioned about steel. See, steel is a very ductile material, and steel is good for earthquake applications. However, our problem is, the connection between steel and other materials. So everywhere, one has to ensure that under the earthquake action, the system is performing well. See, the TMT bar is one material in the whole building. So the system performance can become is really the question. Are you able to understand if the system is performing? Before the TMT bar can break, the system may collapse. So one has to understand at multiple levels. That's why I showed you two examples. One is the system level performance, and another one was the component level performance. In the component, in that Madras Terrace slab, the timber rafter was one material, just one material, right? So there is a material level behavior, there is a component level behavior, and there is a system level behavior. As engineers, we try to see if there is a consistent behavior, an acceptable behavior across all these levels. And that's where engineering tries to do its job. Thank you.
Okay,
Thank you,
thank you.
Thank you, Mr. Shah. So there is one question asked by Mr. Mahavir Raj, but before I read it out, I want to ask Mr. Mahavir Raj that would you want to ask the question yourself, or do you want me to read it out for you? We can do both, but yours is a very interesting question, and it'll be wonderful if you are the one who's asking it. If you could unmute yourself, it's not a compulsion to turn on a video camera, but it's preferred if you do so.
Good morning, sir.
Good morning. Good evening, rather. Sorry.
Good evening, sir. I'm Mahavir Raj from Patna, Bihar.
Yes,
Sir,
please go ahead.
as the as given the vulnerabilities highlighted in low to moderate seismic region, what new research direction do you think we should explore to better understand and protect this historical structure?
Before
Yes.
you answer that, sir, Professor Menon, Mr. Raj, could you give a little introduction about yourself? Like, who are you? Are you a student? Are you a teacher? So we have a better context while
Yeah,
sir answers
yeah,
the question.
I'm a student.
Perfect.
I'm a
Lovely.
student of class 12.
Lovely. Lovely. Sir, if you could please answer, Mr. Raj.
Yes. See, the thing is, you've heard of this statement being made often. Um, Earthquakes don't kill, but buildings do. It's buildings that collapse and that leads to loss of property, loss of life in many cases. Recently, in the end of March, you had this massive earthquake in Myanmar. So the thing is, earthquake intensity can vary from region to region, but as engineers, our responsibility is to ensure that buildings don't collapse if you're looking at a region which is highly prone to earthquakes, or even in regions where low to moderate level of shaking is there. You cannot afford to have buildings collapse and hurt people, right? And that is where some amount of research is essential when we construct. Now, when we construct modern constructions, this knowledge is already going in. We try to construct such that minimum earthquake resistance is available. But all our historical constructions, not necessary that these have been built keeping in mind the possibility of earthquakes, especially in low to moderate earthquake regions where the earthquake activity may be very infrequent. But when it is very infrequent, you and I may not be affected because we will live here for about 70, 80, 100 years, and that's our lifespan. But historical buildings have to be around for centuries, even thousands of years. So very infrequent, rare earthquakes might happen. And in the event of such earthquakes, you cannot lose a historical monument because then you lose hundreds of years of history. And that is where some research is essential to understand what is the minimum safety level that we can guarantee. People should not get affected when such historical constructions collapse. The history must not be lost. And there's some responsibility on us as people who are working in the engineering domain today that we understand these structures. Research is essential to understand the behavior of these structures and also essential to understand what is the type of intervention that we must carry out on these structures. If we are coming up with a solution, let us say you're working with the Taj Mahal, and then you come up with a solution that you have to cover Taj Mahal in concrete to prevent it from getting damaged in an earthquake. That is not an acceptable solution. We have to have a very different solution for a structure which has historical value, and that requires some amount of research and investigations. So all these areas are areas where we have to invest in. Knowledge has to improve in these sectors. Thank you.
So can we take one last question, sir?
Thank you so much, sir.
I've already put spotlight on Mr. Varun Raj. He's actually asked two questions. Mr. Varun Raj, if you could turn on your camera, trust me, it becomes much fruitful for us to interact. If you could please turn on your camera and ask both your questions to sir. Okay, it's okay if you're not willing to turn on your camera. At least if you can unmute yourself and ask, it's absolutely okay. Yes. Varun, are you asking any question? All right, I think he's facing some technical.
You can read the question out quickly.
Yes, I'll do that, sir. I'll do that. Uh, his question is, how do engineers address the challenges of designing safe and efficient high-rise buildings?
Yes. So today we have a much more systematic understanding of how materials behave, how the structure behaves, and more importantly, we have quantitative methods which give us confidence on how these structures are going to be behaving and can be designed. So that's how we are confidently building multi-story constructions. We are building massive bridges simply because using laws of physics, using laws of mechanics, we have been able to create methods that can understand the behavior of these structures under gravity, under wind forces, under earthquake forces, under blast forces, and so on. So today, that is how engineers function. They will create a model of the building on a computer, do complex analysis, be able to check some things by hand calculation, and then start making drawings for it to be constructed. And after it is constructed, go and verify if it has been constructed as it has been designed. So that's how high-rise buildings are being designed, big bridges are being designed in a safe and efficient manner, as your first question. The other thing is, yes, sustainability. Environmentally friendly designs and materials. We are moving towards a world which is going to become more and more scarce in all the natural resources. And therefore, we have to be very, very responsible in the way we use them and the amount that we actually use. And while we make safe structures and efficient structures, we also have to ensure that the carbon footprint of the material that we use and the methods of construction are minimized as much as possible. So today, for example, the use of burnt clay brick, the normal reddish colored bricks, we have stopped using burnt clay bricks so much for modern constructions because the carbon emissions because of firing these bricks to very large temperatures and then using them in buildings is too costly for the environment. We have to use materials which do not have such a large carbon footprint. We are using topsoil to create the brick, and then we are firing the brick to such large temperatures. And therefore, their carbon footprint is very large. So we use other materials, environmentally friendly materials, which do not require firing, which does not require so much of energy, and materials which are possibly even reused from other constructions. Construction waste, demolition waste is reused in modern constructions. And that is the way we try to reduce the carbon footprint, the environmental impact of modern constructions on we have only one Earth, right? And that's how we really have to ensure we are using material in a very responsible manner.
All right, I think that will be all for the questions. But I'll request all of you to please stay tuned for 5 more minutes. I will share the link to download your certificates at the end of it. But before that, we would want to wholeheartedly thank you so much, Professor Menon, for that truly, truly inspiring session. There were some people asking that if there's a link for feedback, and I happy to just share my email ID. And I'm not, I'm not exaggerating when I just said my email ID has suddenly flooded with all the emails I've suddenly received in the past 5 minutes. Everybody saying that it's been such a wonderful and informative session. You took us on a journey, not just across historic monuments, but into the mind of a scientist, from ancient temples to earthquake resistant designs. So you've shown us how curiosity, research, and real world problem solving come together to preserve history and shape the future. To all our students and teachers in the audience today, I hope today's session reminded you that science isn't just about formulas and facts. It is about adventure, it is about asking bold questions, and it is about solving mysteries, and sometimes even saving the world one brick, one monument, one idea at a time. And yes, it is also about taking joy in failure, learning from mistakes, and occasionally watching things collapse, because every fall is a chance to rebuild stronger and smarter. Thank you, sir. Thank you once again for sharing your incredible journey and for reminding us that discovery truly begins with curiosity. Thank you
Thank
so
you
much for
very
your
much.
time.
Thank you very much. It was really an exciting platform for me to interact and thanks to you for this organization and really.
Thank you.
Thank you. Bye bye.
Thank you so much.
Have a nice